Welcome back. Problem 6-16. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by RC Hibbeler. So statement is determine the placement distance A of the roller support so that the largest absolute value of moment is minimum. Draw the shear and moment diagram for this condition. So you can see this is the overhanging beam. Clear, there is a roller support at point B and there is a pin support at point A, and two concentrated load at a length of L by 2 and at a length of L from point A. Clear? And the condition is given that you have to find this placement of roller support B. You have to find this A for the condition that largest absolute value of moment is minimum. So let's start with the solution. So first step is that if you remove this pin support at point A, so you will be having a reaction force, let this is equal to RA, and if you remove this roller support at B, you will be having a reaction force which is represented as RB. So we'll find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0 and taking the counterclockwise moment as positive. So about point A, first moment is this P into perpendicular distance is L by 2, and this is producing clockwise, so it will be negative. So I will write minus P into L by 2. The second moment that is about point A is this P, and perpendicular distance is this one, which is L by 2 plus L by 2, and that is L. And this is also producing clockwise, so it will be negative. So minus P into L. The third moment that is produced due to this RB into perpendicular distance is this A, and it is producing counterclockwise movement, so it will be positive. So I will write plus RB into A. Their sum must be equal to 0. So from here I will get minus 3PL over 2 plus RB into A is equal to 0. So from here you will get this RB will be equal to 3PL over 2A. So you have RA. Now you can find RB by using equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So RA, which is upward, plus RB, which is 3PL over 2A, minus P, which is downward, and minus P. So minus 2P is equal to 0. So from here you will get RA will be equal to 2P minus 3PL over 2A. Now we will find this absolute minimum. I will write it absolute minimum moment. So for that I will have criteria which we will write that maximum positive moment is equal to maximum minimum moment. This is the condition for absolute minimum moment. Maximum moment positive will be equal to maximum minimum moment. So you can see here at this point we will have a maximum positive moment. We will calculate it, and at this point we will be having maximum moment that will be negative, and we will then equate it. So for that I will section the beam at a distance of L by 2 and draw the free body diagram. So let me draw the beam first. This is here at this point we will be having RA, clear, which is upward, and this RA is equal to 2P minus 3PL over 2A. This distance is L by 2, clear, this is L by 2. And when you cut it, you will be having a shear force that will be acting downward, and you will be having a moment in counterclockwise direction. Clear? And this is its neutral axis. This is the neutral axis. So we'll find this maximum positive moment by using equation of equilibrium, that sum of all moments about neutral axis must be equal to 0, taking the counterclockwise movement as positive. So about this, we have one external movement is this one, and the second one is RA into perpendicular distance is L, and it is producing clockwise. So it will be negative and this will be positive. Their sum must be equal to 0. So I will write maximum positive moment minus 2p minus 3p L over 2a into perpendicular distance is L by 2. Their sum must be equal to 0. So from here you will get maximum positive moment will be equal to, it will be 2pl over 2, that will be minus, and when it will go toward right side it will be plus, and the other one will be minus 3pl square over 4a. So it will give you maximum positive moment will be equal to p into L minus 3pl square over 4a. Clear? So this is maximum positive moment. For minimum positive moment, we will cut the beam at B, because at this region we will be having a minimum maximum moment that is negative. So you can see here this distance is L, clear, and this is A. So this distance will be equal to L minus A. So we'll draw the free body diagram for the remaining this portion. Let this is the portion that is L minus A, clear, L minus A. At this point we have a load which is P. I will show you here. You can see this is the P that is acting. So when you cut the beam, you will be having a shear force in upward direction, and you will be having a moment that will be a clockwise, and this moment will be maximum moment, that will be minimum, clear, and this is the neutral axis. So we'll find this maximum moment minimum by using equation of equilibrium, that sum of all moment about neutral axis must be equal to 0, and taking the counterclockwise moment as positive. So again you can see this is a clockwise movement, so it will be negative, and this is P into perpendicular distance is L minus A. So it will be producing counterclockwise, so it will be negative. And this movement is counterclockwise, so it will be positive. So I will write maximum moment that will be negative minus P into L minus A is equal to 0. So it means that maximum moment that is negative is equal to P into L minus A. Now we will use this condition, clear, in order to find the placement A for the roller support B. So maximum moment positive will be equal to maximum moment negative, clear. So maximum moment positive is P into L minus 3p L square over 4a is equal to P into L minus A. So we will get LCM, or you can multiply 4a on both sides, so it will be equal to 4a into PL minus 3pl square is equal to 4a into P into L minus A. And you can see P is available in all the terms, so divide P on both sides, so you will get 4al minus 3l square is equal to 4a into L minus A, or that will be equal to 4al minus 4a square, 4al minus 3l square. So you can see this will cut with this, so we will have 3al square minus 4a square is equal to 0. Or you can say that 3l square is equal to 4a square, clear. So we have to find A. So A square is equal to 3 over 4 L square. And if you take square root on both sides, so you will get A will be equal to 3 over 4 L square under the root, and we will get it under the root 3L over 2. So this is the value of A, and this A will be equal to 0.886 L. I will write it over here. A will be equal to 0.886 times length. So this is how we will find A for the placement of roller support. Now we will solve. When we have solved first part, we will move towards second part. Draw the shear force and bending moment diagram. So when you put A is equal to put A is equal to 0.886 L in RA and RB, RA and RB. So you will get RA will be equal to here. From here you will get RA will be equal to 0.268 times P, and RB will be equal to 1.732 times P. So what you have to do, you have to put the value of A here and A here. So you will get RA will be this one and RB will be this one. Now we'll move toward shear force and bending moment diagram. For that I will take the vertical lines from the end of this beam. First we will draw the shear force. So there will be horizontal line which will show the length in X. Okay, here we have shear force. Clear? Now you can see at point A we have only RA which is equal to 0.26 P. So let each division is 0.2. This is minus 0.2, minus 0.4, minus 0.6, minus 0.8, and minus P. Clear? And same 2, 3, 4, and 5 we will be having a P. Okay, starting from the first point RA which is 0.26 P, so it is upward, so this will be the point. And moving from this till point B, there is no other shear force, so it will remain same. It will be like a horizontal line, 0.268 P. Now you can see here you have a P that is minus downward. So 0.26 P minus P will be equal to minus 0.732 P. And it will move downward to minus, let minus 0.72 P is at this point. So it will come downward. Not till this point, till point P. So I correct it. I will go backward. So this is the point. So okay, this is, if you trace it, okay, so first your point will be this one. This is 0.268 P, this point. And now from here it will go down to 0.72 P minus 0.732 P. And from B to the roller support it will remain same horizontal. At this point you have RB which is equal to 1.372 P. So this plus 1.732 P will give you P. So shear force will change from this point till to the P, and it will change to this P. This is the point P. You can see this is the P. Clear? And moving from point P till end, we do not have any shear force, so it will be horizontal. And at this point you can see you have minus P. It will cause it to 0. Clear? So this is your shear force diagram. Now we will draw the bending moment diagram. So for that I will draw a horizontal line to show the X, and here we will having movement. So first area under the shear force diagram will give you the moment. So this is the height and the length is L by 2. So 0.268 multiplied by L by 2 will give you the moment, and that will be equal to 0.268 multiplied by L by 2 will give you 0.134 P into L. Clear? So we'll plot this. So let this is 0.1 P into L. This is 0.2 P into L. And similarly minus 0.2 PL minus 0.2 PL. This is 0.1. Okay. So first point is 0.134. So 0.134 at this point we have moment is equal to 0. And if you project this, so 0.134, let this is the point 0.134 P into L. And you can see that shear force is a horizontal line. So bending moment will be 1 degree higher and slope will be increasing because this area is positive. So I will join this. Okay. So this is the first point. Now second area is this one, and this area is equal to minus 0.372 P into this distance, which is equal to L by 2 minus A, and A is 0.866 L. So you can calculate it, and you calculate this area will be negative, and this when added with this area will give you minus 0.314 P into L. So you can plot it minus 0.134. Let this is the point. So it will be like this. So this point is minus 0.134 P into L. Now next area is this area, and this area you can see this is P. Clear? And this distance is L minus A. So L minus A is 0.886, which is equal to 0.134 plus 0.134 P. And when you L, and when you multiply it with P will give you plus 0.134 P into L. So the moment will be 0 at this point. Since this shear force is a horizontal line, so bending moment will be 1 degree higher and slope will be increasing. So this is its bending moment diagram, BMD, and this is its shear force diagram for this condition. And that was all about this problem 6-16. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-17. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by RC Hibbeler. So statement is express the internal shear and moment in the cantilever beam as a function of X, and then draw the shear and moment diagram. So you can see this is the cantilever beam which is having a point load at this end, and there is a triangular load from start till the end, that is 200 pound per feet, and at this end we have a fixed support. Clear? So you have to first find the internal shear and moment as a function of X, and then draw the shear force and bending moment diagram. So let's start with the solution. So if you remove this fixed support at point A, so you will be having a reaction force which will be represented as RA, and you will be having a moment which will be represented as MA. So we will find this RA and MA by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So you can see one force, that is 300 acting downward, so minus 300, and you can see there is a there is a triangular load. So when this load is converted into point load, so it will be equal to minus, because it is downward, so minus 100 1 over 2 into 200, and the length over which it acts, which is 6 feet. I will also represent it over here. This will be like this. 1 over 2 into 200 multiplied by 6. And that will be equal to 1200 divided by 2, which is 600 pounds. And this point load will act at a distance of L by 3. And L by 3, L is 6 feet. So L by 3, 6 divided by 2 is 6 divided by 3 is 2 feet. So 2 feet from this denser side. This is the denser side. Clear? So remaining will be equal to 4 feet. And the third load is RA, which is upward. So RA will be equal to 0. So minus 300 minus 6 to 12 divided by 2 is 600 plus RA is equal to 0. So it means that we have this reaction force RA is equal to 900 pound. Now we will find this moment MA by using equation of equilibrium, that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, one moment will be this force into perpendicular distance is this 2 feet, and this is producing counterclockwise movement, so it will be positive. So I will write 600, which is the load, into 2. That second moment that is produced due to this force 300 into perpendicular distance is 6 feet, and this is also producing counterclockwise, so it will be positive, plus 300 multiplied by 6. And the last movement is this external movement, which is clockwise, and that is MA, and then MA is equal to 0. So MA is equal to 1200 plus 1800, and this MA will be equal to 3000 pounds into feet. Now you have both RA and MA. So what we will do, we will go to solve first part, that express the internal shear and moment as a function of X. So what we will do is that we will cut the beam at any distance of X. X will be this distance, and we will draw the free body diagram. So if I draw it over here, so this is the distance X here. This is distance X. At this point, we have a load of 300 pound. Clear? And there is a uniformly or triangular load like this. Clear? Now you can see the load over here is 0, and here it is 200 over a length of 6 feet. So what will be the load at this point? What will be the W value? So for that, I will take 200 is this value divided by whole length, which is 6 feet, and is equal to W divided by length, which is X. Because these are two similar triangular, you can see one triangular is this one, and the second one is this one. So by taking the ratio of their side, we will find this W. So W will be equal to 200 into X divided by 6, and that will be equal to 33.3x. So this will be the magnitude of this W at this point. So W is equal to 33.3x. Now we will, as we have cut the beam, so you will be having a shear force, clear, which is V, and you will be having a moment which is equal to M. So we'll find this V and M by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. Okay. One force which is 300, that is downward, so minus 300. The second force, which is this triangular load, and when this is converted into a point load, so it will be equal to 1 over 2 into 33.3x, and the length, which is X. The length is X. So I will write minus 33.3 3x divided by 2 into x. Clear? And the another force is this shear force, which is minus v, is equal to 0. So from here you will get this v is equal to minus 300, and this will be equal to minus 16.67 x square, and the unit will be in pound, and this is the required shear force equation in term of x. Now we'll find this m. So for that I will apply sum of all moments about this, let's say point O is equal to 0, and taking the counterclockwise moment as positive. So first moment is 300 into perpendicular distance is x, and this is producing counterclockwise moment, so it will be positive. Clear? So I will write it 300 into x. The second moment is due to this load, which is 1 over 2 into 33.3x multiplied by x, and the perpendicular distance will be now this. And this is the L by 3. L here is length is x, so x by 3. And this is also producing counterclockwise movement, so it will be positive. So I will write plus 1 over 2 into 33.3x into x. Clear? Into perpendicular distance is x by 3. Okay. And there is a moment, external reaction moment, which is counterclockwise moment, so it will be also positive. So from here you will get this moment will be equal to minus 300x, and the remaining will give you minus 5.556x cube, and its unit will be pounds into feet. So this is the moment equation in term of x. So we have solved our first part. Now we'll move toward the second part, is to draw the shear force and bending moment diagram. So I have to copy this and paste over here. Okay. Now for bending moment and shear moment diagram, let me resize it. What we are going to do is that you will take the vertical lines from the end of this beam. Clear? Similarly from this end, and horizontal line in order to show the length, that is x in feet. Here we will draw the shear force, that will be in pounds. Okay, so we have I will draw tables for x, shear force and moment. So for x is equal to 0, for 1, for 2, for 3, for 4, for 5 and 6. So when you put x is equal to 0 in this equation, so you will get shear force is minus 300, unit will be pounds, and here unit will be pounds into feet. Similarly for x is equal to 1, put it in this equation, so you will get minus 316.67. For 2 it will be minus 366.68, minus for x is equal to 3 feet it is 450.03. For x is equal to 4, minus 566.72. For x is equal to 5 it will be minus 716.75, and for x is equal to 6 it is minus 900 pounds. Okay, same is if you put the value of x in this moment equation. Clear? For x is equal to 0, this will give you 0. For x is equal to 1, minus 300, 5.56. Similarly, minus 644.4, minus 1050.12, minus 1555.84, minus 2195, and for x is equal to 6 it will be minus 3000. Now you have all these values. So first we will focus on shear force. Let this division is equal to minus 200. Let you can choose your own scale. Minus 400, minus 600, minus 800 and minus 1000, and you can plot this point. So at x is equal to 0, we will have a first point over here. Let this is the half of the beam. This is the half of the beam. So at half means 3 feet. So we have minus 450. So minus 450 will be over somewhere here because mid is 500. So 450 is this one. Minus 450. And at end we have minus 900. So minus 900 will be this one. As the shear force equation is a second degree curve, you can see this is a quadratic equation. So your this shear force will be in second degree curve. Okay, at this point we have 300. So this is the first point, which is this, which is minus 300. At x is equal to 0, we have minus 300. So your shear force will be like this one. This will be a curve. Clear? This will be a curve. That is shear force diagram. You can locate all other values if you have a graph paper, so you can locate all these points, but I have done it directly. Now we'll draw the moment diagram. So for moment diagram, again you have to take a horizontal line that will show x in feet, and here you will have a moment that will be in pounds into feet. Okay, so here we will take one division is equal to for example 500. So minus 500 minus 1000. Similarly this is minus 2000 and this will be minus 3000, which is this one. Okay, at here one thing is that you have minus 900, and at point RA we have a load of RA, which is plus 900. So minus 900 plus 900 will bring it to this point 0. So this will complete your shear force diagram. Okay, for bending moment diagram at x is equal to 0, so your first point will be this one. You can see at x is equal to 0, we have moment is equal to 0. At x is equal to 3, we have 1050. So 1050 at x is equal to 3. Let this is the point, minus 1050. Okay, 0.12 pounds into feet, and at x is equal to 6, this is minus 3000. Now you can see that this moment equation is third degree equation, so it will be curve, and we will obtain it by joining this in like this in curve form. Clear? And this is your, this is minus 3000, and at the end you can see you have a moment that is clockwise. So while drawing it on a bending moment diagram, it will go upward to bring it to the 0. Clear? And that is your bending moment diagram. You can plot each and every length and its value over here if you have a proper length and you have a graph paper as well. So this will give you the same values. And that was all about this problem 6-17. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then I will request them to subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. Problem 6-18. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by RC Hibbeler. Statement is draw the shear and moment diagram for the beam and determine the shear and moment throughout the beam as a function of x. So you can see this is a cantilever beam that is acted upon by uniformly distributed load over a length of 6 feet, and at 6 feet we have a point load of 10 kips, and at this end free end we have point load of 8 kips and external moment of 40 kips into feet. So you have to determine the shear and moment diagram of the beam and shear and moment throughout the beam as a function of x. So let's start with the solution. So first step is that if you remove this support, fixed support at point, let this is point A, So you will be having a reaction force which will be equal to RA, and when you remove this you will be having a moment, reaction moment as well, MA. So we'll find first MA and RA by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0 and taking the counterclockwise moment as positive. Now you can see this is a uniformly distributed load of 2 kips. So when this 2 kips per feet uniformly distributed load is converted into a point load, so I will take this load into length over which it act, which is equal to 6, and that will be equal to 12. Clear? Now we'll apply this equation of equilibrium. So at about point A, first movement will be this load into perpendicular distance will be 6 divided by 2 because it will act at a half. So this will be 3 feet, and that will be clockwise, so it will be negative. So I will write 12 into 3 minus 12 into 3 minus 12 into 3. The second movement about point A is this 10 kips load into perpendicular distance is this 6 feet, and this is also clockwise, so it will be negative. So minus 10 into 6. The third moment that is produced due to this 8 into perpendicular distance is this 10, and this is also clockwise, so it will be negative. So I will write minus 8 into 10, and this clockwise external moment which is minus 40 plus this external moment which is counterclockwise MA will be equal to 0. So when you solve this, you will get this moment about point A will be equal to 216 kips into feet. So this is moment about point A. Now we'll find this RA by using equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see RA which is acting upward. So RA minus this point distributed load converted into point load. So minus 12 minus 10 which is this one and minus 8 will be equal to 0. So from here you will get RA will be equal to 30 kip load. Okay. Now first we will solve this shear and moment function. Shear and moment as function of x. So for that, if I cut beam at a distance of x and draw the free body diagram, so it will be like this. This is the beam. Clear? Here you have RA which is 30 kips, and this distance is where you have cut the beam is x, and there is a moment which is MA, and that is 216 kips into feet, and from here from throughout the length of x we have uniformly distributed load that will be acting downward, and this load is 2 kips per feet. And when you cut it, so you will be having a shear force there which is V, and you have a moment, reaction moment M. So we'll find this V and M by using equation of equilibrium. So we'll, and this is for x is great, this is valid for x is greater than 0 and less or equal to 6 feet. Clear? Because over this we have uniformly distributed load. Now we will find this V and M by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So 30 which is acting upward, so 30 minus this V which is acting downward, and when you convert this uniformly distributed load into point load, so 2 into length which is x, and that will be acting downward, minus 2 into x will be equal to 0. So from here this shear force will be equal to 30 minus 2 into x, and unit will be kip. Let this is your equation number 1. Now we'll find this m. So for m we will apply sum of all moments about point. Let this is point O. So point O is equal to 0 and taking the counterclockwise movement as positive. So about this point O, first movement will be, it is 30 into perpendicular distance is x. This is clockwise, so it will be negative. So I will write it first, minus 30 into x. The second movement will due to the second movement is this external movement which is counterclockwise, and this is 216. So I will write plus 216. The third movement will be due to this 2x, and it will be acting at a half of this total length, which is equal to x by 2, and this is producing counterclockwise movement, so it will be also positive. So I will write 2x into x by 2. So plus 2x into x by 2, and there is an external movement which is again counterclockwise, m is equal to 0. So from here we will get minus 30x plus 216, 2 will cancel, and plus x square plus m is equal to 0. So this movement will be equal to minus x square plus 30x minus 216. So this is a moment function which is a function of x, and unit will be kips into feet. Let this is equation number 2. Now equation 1 and 2 are valid for x is greater or equal to 0 and less or equal to 6 feet. You can see this is valid till this point. Okay, what we will do is that now we'll cut the beam for x is equal to this. So this will be the total x. Clear? X is this one. So this remaining distance will be equal to, total length is 10 feet. So 10 minus x will be this remaining portion. And we will draw the free body diagram of this portion. So let me draw it. And this is region for x is greater than or equal to, x is greater than 6 feet and less or equal to 10 feet. And when you draw the free body diagram, it will be like this. So at this end we have a point load of 8 kips. There you have a moment of 40 kips into feet, and when you cut it you will be having a shear force upward, and you will be having a reaction moment m. Clear? Just check it like this. I have drawn this portion over here, and we will find this shear force and moment by using equation of equilibrium, that sum of all forces in a y direction must be equal to 0 and upward force is taken as positive. So you can see v is upward, so v minus this 8 which is downward is equal to 0. So it means that shear force is 8 kips for the length greater than 6 feet and less than 10 feet. Now we'll find this moment. So for moment sum of all moments, let this is point number 2. So about point 2 is equal to 0 and taking the counterclockwise moment as positive. So you can see this remaining distance was 10 minus x. So about point 2, the first moment will be 8 into perpendicular distance is 10 into 10 minus x, and this is clockwise, it will be negative. And this minus 40 kips into feet, that is also clockwise, and plus this external movement which is counterclockwise, this will be also negative, and their sum must be equal to 0. So I will write minus m minus 8 into 10 minus x, 10 minus x, and minus 40 is equal to 0. So this moment will be equal to minus 80 plus 80x minus 40. So it will be equal to 80x minus 120, and unit will be equal to kips into inch. This is your equation number 3 and this is your equation number 4. Now equation number 3 and 4 are valid for x is greater than 6 feet and less or equal to 10 feet. So these are the shear force and moment equation as a function of x for the region x is greater than or equal to 0 and less or equal to 6 feet, and these are the shear force and moment equation for region x is greater than 6 feet and less or equal to 10 feet. Now we'll move towards second part, which is draw the shear and moment diagram for the beam. So for that, again I have to draw the vertical lines from the end of this beam. So let me draw it first. At this end I will also draw vertical lines, and from this end also, and we will draw a horizontal line in order to show the length. So this is length, and we will write this x will be in equal to feet, and y-axis we have shear force, the unit will be kips. Okay, so let one division is 10, so 10, 20, 30, so you can take as per your own, clear, and similarly minus 10, minus 20, and so on. So at first point we have RA, which is equal to 30 kips. So first point will be your this one. This is your first point. Now at a distance at this point at a length of 6 feet, you can see you have distributed load. So 2 into 6 will be minus 12. Clear? So what we will do is 30 minus 12 will be equal to 18. So at this point we have 18. Clear? So we'll plot this point. Let this point is 18. Now you can see that your distributed load is a horizontal line with 0 degrees. So shear force will be 1 degree higher, and it will be linear line, and slope will be decreasing because this load is downward. So I will join these 2 points using a straight line. Now at this point we have minus 10, so minus 18 minus 10 will bring it to 8. So shear force will change to this point 8. This is 8. Clear? And moving from this point till end, there is no other shear force, so it will remain horizontal. Clear? And at the end you can see you have minus 8. So plus 8 minus 8 will bring it to 0. And this will be your shear force diagram. Now we will move toward bending moment diagram, and for bending moment diagram I will draw a horizontal line to show the length in feet, x in feet. Okay, so here we have moment, which unit will be kips into feet. Let one division is equal to 50, minus 100, minus 150, minus 200, and minus 250. So at x is equal to 0, we have moment will be equal to 0. This is your first point. Now second point will be the area under the shear force diagram will be this one. You can also use, this is a trapezoid, you can also calculate it, but we have a function here for the moment. So you can see for x is equal to 6 feet. So when you put x is equal to 6, so 30 into 6 square minus, and this will give you moment will be equal to minus 72. So okay, so before that we can see that we have a moment ma at this point. There is no moment 0 because there is external moment ma is given, which is equal to 216, that is counterclockwise. So while drawing the bending moment diagram, it should be causing the bending moment toward the negative side. So let this is minus 216. So minus 216. This will be your first point. Now for x is equal to 6 feet. So when you put it in this formula, so you will get moment will be equal to you will get the moment minus 72. For x is equal to 6, it will give you moment 72. So it means that our length of 6 feet we have minus 72. So we'll plot this, let this is minus 72. Clear? Now you can see that this shear force is a linear line of first degree and slope is decreasing. So bending moment will be second degree line and it will be counterclockwise like this. Clear? So we will join these 2 points like this. It will be a second degree line. Clear? This will be the line. Now the second area under the shear force diagram is this area. You can also calculate that, but for x is greater than 6 feet and less than 10, less or equal to 10 feet. So you will use this equation. So when you put x is equal to 10, clear? So this will be equal to 800, sorry, this is not 80, this is 8x. So let me correct it, minus 80 plus 8x. So this is 8x. So for x is equal to 10, clear, we have 8 into 10 minus 120 will be equal to minus 40 at this point. Clear? So we will plot this minus 40. So minus 40. And you can see that this shear force is a horizontal line with 0 degree. So bending moment will be 1 degree higher and this is positive. So slope will be increasing. So we'll join these 2 points like this. Clear? And at the end you can see you have a movement that will be clockwise, so which will cause it toward minus 40 plus 40 will be equal to 0. So this will be like this. So it will be your bending moment diagram. So this was all about this problem 6-18. You can find this shear force and bending moment diagram. So if you put x here and here, so you will get, and when you join all these points, so you will get the shear force diagram like this and the bending moment diagram will be like this. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Hello friends, welcome back. Problem 6-19. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by RC Hibbeler. So statement is draw the shear and moment diagram for the beam. So you can see this is overhanging beam and from this end we have a uniformly distributed load of 2 kips per feet, and at this point we have external moment of 3 kips, 30 kips into feet. So there is a roller support at point A and a pin support at point B. So you have to determine shear and moment diagram for the beam. So let's start with the solution. So if you remove this roller support at point A, so there will be a reaction force. Let this is represented as RA. And if you remove this pin support at point B, so you will be having a reaction force which is represented as RB. So we'll find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0 and taking the counterclockwise moment as positive. So we will convert first this uniformly distributed load into a point load. So it will be equal to 2 into the length over which it acts, that is 10. And it will act at a half of total length. So 5 divided by 2 is, this distance is 2.5 feet. Clear? Okay. Now sum of all movement about point A is equal to 0. So first movement will be 2 into 10 into perpendicular distance is this 2.5 feet, and it is producing counterclockwise movement, so it will be positive. So I will write it 2 multiplied by 10 multiplied by 2.5. The second movement, that is this external movement, this is clockwise, so it will be negative, so minus 30. And the third movement, which is due to this RB into perpendicular distance, is this 10 feet, and this is producing counterclockwise, so it will be positive. So plus 10 times RB is equal to 0. So when you calculate it, you will get RB will be equal to 0.5 and unit will be kip. Now we'll find this RA by using another equation of equilibrium, that is sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So 2 into 10, which is acting downward. So this is minus 20. Clear? Sorry, this is not 10. This is 5 because this distance is 5. This is 5. So 2 into 5. So correct it over here. 2 into 5. Okay, so it will give you 0.5. So minus 20 into minus 2 into 5 will be equal to minus 2 into 5 will be equal to minus 10. So minus 10 plus RA, which is upward, plus RB, which is upward, equal to 0. So minus 10 plus RB is 0.5 plus RA is equal to 0. So from here you will get RA will be equal to 9.5 and unit will be kip. Clear? So we have both RA and RB. So RA is 9.5 kip and RB is 0.5 kip. Now we'll plot the shear force and bending moment diagram. For that I will draw vertical lines from the end of this beam. Clear? So let me draw it. This is the vertical line from here, and also from here we will draw vertical line. Clear? And at each length we will also draw lines. Same is the case for here. We'll draw vertical line. Okay. Now we'll draw horizontal line in order to show the length. Clear? So this will be x in feet. On y-axis we have shear force, which will be in kip. Clear? So one division will be equal to plus 5. So plus 5 plus 10 minus 5 minus 10 you can take as per your scale. So at first point you can see you have shear force at x is equal to 0. So we will first point will be this one. Okay. So at a length of 5 feet, so 2 into 5 will be minus 10 because it is downward. So here the shear force will be minus 10. So second point will be this one. Clear? Minus 10. Now you can see that this uniformly distributed load is a horizontal line with 0 degrees. So and that is downward negative. So bending moment, shear force will be 1 degree higher and its slope will be decreasing, and it will be first degree line. So I will join these 2 points. Clear? Now at this point we have RA. Clear? Which is 9.5. So minus 10 plus 9.5 will give you minus 0.5. So we'll plot it minus 0.5. So let's say minus 0.5 is this point. For example, minus 0.5. So shear force will change from minus 10 to minus 0.5. Okay. Now moving from point A till B, there is no other shear force, so it will remain same till this end. Clear? So this shear force will remain same till this end. And at the end you can see you have RB, which is plus 0.5. So minus 0.5 plus 0.5 will bring it to 0. So this will be like this. Clear? So this is your shear force diagram. Now we'll draw the bending moment diagram. So for bending moment diagram, again I have to draw a horizontal line. Clear? And here we will, x will be in feet, and we will, on y-axis we have moment that will be keeps into feet. Okay, so one division will, let's we take one division as 5. Clear? So this is plus 5, this is minus 5, minus 10, minus 15, minus 20, and minus 25. So area under the shear force diagram will give you bending moment. So first area, you can see this is a triangle. So this area will be equal to 1 over 2, this height which is minus 10, and this length which is plus 5. Clear? So it will give you minus 25. So first point will be minus 25, and minus 25 is this point. Clear? Okay, at x we have moment is equal to 0. So you can see that shear force is a linear line, first degree line, and slope is decreasing. So bending moment will be 1 degree higher, which is, it is a second degree line, and the slope will be decreasing, and it will be in clockwise direction. So it will be like this. So let me join this in curve form. It will be like this. Okay, now second area under the shear force diagram will be this area. You can see this area is, this is rectangle, so it's minus 0.5 into this length which is 5 will give you minus 2.5. So minus 25 and minus 2.5 will be equal to minus 27.5. So at this we will have minus 27.5. So we will locate, let minus 27.5 is this one, for example, minus 27.5. Now you can see that shear force is a horizontal line with a 0 degree, and it is a horizontal line with a 0 degree. So bending moment will be 1 degree higher, and this is negative area, so slope will be decreasing. So it will be a straight line joining these 2 points. So let me join these 2 points using a straight line. Okay. Now the third area is, okay, at this point you can see you have external movement of 30 kips into feet, which is clockwise. So while drawing the bending moment diagram, clockwise will cause it to move in positive direction, means you have to add plus 30, which is equal to 2.5. So this shear force will change from minus 2.75 to 2.5. So let this is the point where we have 2.5. So your shear force bending moment will change from minus 27.5 to 2.5. Now the last area is this area, and this area is, you can see the height is 0. Minus 0.5, and this distance is 5. So 5 into minus 0.5, clear, will give you minus 2.5. So plus 2.5 and minus 2.5 will cause it to 0 at this point. And this, the line will be like this, because the shear force is a horizontal line with 0 degree, and this area is negative. So this will be first degree line, and slope will be decreasing. So we will join straightforward these 2 points. So you have to join these 2 points like this, and this will give you its bending moment diagram. Clear? And that was all about this problem 6-19. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-20. This problem is taken from chapter number 6 and that is bending and book name is Mechanics of Material by RC Hibbeler. So statement is draw the shear and movement diagram for the beam. Here it is written as overhanging beam, but it is not overhanging beam, it is simply supported beam. So this is the beam AB, clear, and there is a pin support at point A and a roller support at point B. And there is a triangular load from A till length of 12 feet from this end A, which is 3 kips per feet. So here the load is 3 kips per feet. Here this is 0. So we have to draw the shear and movement diagram for the beam. So let's start with the solution. So if you remove this support at pin support at point A, so you will be having a reaction force like this is RA, and if you remove this roller support at point B, so you will be having a reaction force RB. So pin support at A and roller support at point B. So we'll find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see RA and RB which are acting upward. So I will write RA plus RB, and you can see this third load is the triangular load. So we will convert this triangular load into point load. So I will write 1 over 2, 3 kips per feet into length 12 feet. So that will give you 18, 12, 12 36 divided by 2 is 18. So it is 18 kip load. And this will act at a distance of L by 3. So L is 12. So 12 by 3 is 4 feet. So from this side. And this remaining will be equal to 8 feet. So I will write minus this 18 kips load is equal to 0. So it means that RA plus RB is equal to 18. That this is your equation number 1. Now we'll apply another equation of equilibrium that sum of all moments about point A is equal to 0, taking the counterclockwise movement as positive. So about point A, one moment will be due to this load which is 18 kips into perpendicular distance is 8, and this is producing clockwise movement that will be negative. Clear? And the second moment will be due to this RB into perpendicular distance is 18, and this is producing counterclockwise movement, so it will be positive. And the sum of their all this movement about point A will be equal to 0. So I will write RB into 18, which is counterclockwise, minus 18 into 8 is equal to 0. So it means that 18 RB is equal to 18 multiplied by 8. So from here you will get RB will be equal to 8 kip. Now you have this RB is equal to 8. So put RB is equal to 8 kip in equation 1. So you will get RA will be equal to 18 minus 8 will be equal to 10 kip. Now you have RA and RB. So what we are going to define the shear and moment functions. Let me choose another color. Shear and moment function for different region. Clear? So first we will define it for x is greater than or equal to 0 and less than 12 feet. So it means that x is here 0 and x is here 12. So in between this region we will cut this beam. So if I cut it in this region, clear, at any point, for example at this point, and draw the free body diagram, so it will be like this is the beam. Clear? Here you have RA which is 10 kips, this is distance x, where you cut it and there is a uniformly decreasing load at these points there. And when you cut it, you will be having a shear force V and there will be a moment M as well. Now what will be the magnitude over here, which is W? So you can see you have two similar triangle. One is this one clear and the second is this one. So what if we take the ratio of their side? 3 is this one clear, 3 is this one, so 3 divided by total its length 12 will be equal to, here the magnitude will be W, so W divided by X. So from here we will get W is equal to 3X divided by 12, which means that X by 4 clear. So here W is equal to X by 4 kips per feet. Okay, now we will find this M and V by using equation of equilibrium. So if you convert this triangular load into a point load, so it will be equal to magnitude which is X by 4. This is 1 over 2 into X by 4 into the length over which it acts, that is X clear, and that will act at a distance of X by 3 from this side, and this remaining will be 2X by 3. Now we'll apply equation of equilibrium that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see V is downward, so minus V minus this load 1 over 2 into X by 4 into X is equal to 0. And there is also 10 load which is upward, so I will write plus 10 over here. So from here V will be equal to 10 plus 10 minus X square over 8, and unit will be kips. That this is your equation number A clear. Now I'll find this moment, so sum of all moment, let this is point O, about point O is equal to 0 and taking the counterclockwise moment as positive. So about this point O, one moment will be due to this load into perpendicular distance is X by 3 and this is producing counterclockwise moment, so it will be positive. The second moment will be this counterclockwise which is external moment, and the third moment will be 10 into perpendicular distance is X and this is producing clockwise, so it will be negative. So I will write the sum must be equal to 0. So M is positive plus 1 over 2 into X by 4 into X into perpendicular distance X by 3 and minus 10 into X will be equal to 0. So M, when you solve this, you will get M is equal to 10X minus X cube over 24. And the unit will be kips into feet. That this is equation number B. Now equation A and B are valid for X is greater than or equal to 0 and less than or equal to 12 feet. So again, now here we will take another section at this point. So this distance total is 18 feet and let this distance is X. So this remaining distance will be equal to 18 minus X. So we will focus on this portion clear and we will draw the free body diagram. So for region X is greater than 12 feet and less or equal to 18 feet. The free body diagram will be like this. So at point B, we have 8 kips load. This is point B. So 8 kips load. And when you cut it, you will be having a shear force here upward. Clear? And there will be a moment as well. This distance is 18 minus x. Now we'll find this shear force V and M by using equation of equilibrium. So sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So V upward plus this 8 is upward is equal to 0. So V is equal to minus 8 kip. Clear? So it means that your shear force is minus 8 at this point. Now we'll find this moment, that sum of all moment, let this is your point, this is your point E. So let sum of all moment about point E is equal to 0 and taking the counterclockwise moment as positive. So external moment which is clockwise, that is minus M, and this due to this load 8 into perpendicular distance is 18 minus x, and it will be counterclockwise, it is positive. So plus 8 into 18 minus x will be equal to 0. So from here this moment will be equal to 8 into 18 minus x, and the unit will be kip into feet. This is your equation number 3 and this is your equation number 4. So equation 3 and 4 are valid for x is greater or equal to 0 and 12 feet, and less or equal to 18 feet. So using this equation we will draw the shear force and bending moment diagram. So for that I will draw the line from the end of this beam. For example, this is the line from the end of this beam, and from here you will be also having a line. Clear? Now you will draw a horizontal line to show x in feet, and here on y-axis you have shear force in kip. Let each division is of 5. So 5, 10. Similarly minus 5, minus 10. Okay. Now for x is equal to 0. For, I will write over here, for x is equal to 0, put in equation 1. So you will get, this is equation number A, not 1 in this. So you will get V is equal to 10. So your first point will be this one on shear force. At x is equal to, this point is 12 feet, here 12 feet. So at x is equal to 12 feet, put in equation number A. So when you put it in this equation, this is the equation, so you will get shear force will be minus 8. So at this point you have, this is minus 8. This point is minus 8. And at this equation can be used for x is greater or equal to 0 and less or equal to 12. Now for this side we will use this equation, V is equal to minus 8 kips. So here greater than 8 it will remain same till minus 8, and at end you can see you have plus RB which is plus 8. Now you can see that this shear force, this triangular load is downward, and this is first degree line. So bending moment will, shear force will be second degree curve, and the slope will be decreasing. It will be like this. Okay, and then moving from 12 feet to end, there is no other any shear force, so shear force will remain same. And at point B we have RB which is upward plus 8. So this will be your shear force diagram. Now you can see here the shear force is 0, clear, at this point. So we will find this location. So what we will do is that put V is equal to 0 in equation A. So you will get 0 is equal to 10 minus x square over 8. And when you solve this, you will get x will be equal to 8.944 feet. So this means that this point is 8.944 feet, where shear force is 0. And at this point, the bending moment will be the maximum. Now we will draw the bending moment diagram. So for bending moment diagram, I will take a horizontal line which shows x in feet. And here you will be having moment, and unit will be kips into feet. Let each one is of 5, 10, 10 kips, 10, 20, 30, 40, 50, and this one is 60. So at x is equal to 0, put in equation number B. Equation B is for moment. For region x is greater than 0 and less or equal to 2 feet. So moment will be equal to 0. So your first point will be this one. Now at x is equal to this length. X is equal to 8.944 feet. Put in equation number B. So you will get the maximum bending moment, and that maximum bending moment will be equal to 59.6 kips into feet. So we'll plot that point. Let this is the point. So 59 point will be somewhere here. 59.96. Now 59.6 kips into inch. Now at distance of 12 feet, put x is equal to 12 feet in equation B. So you will get moment will be equal to 48. So at x 48 is this point. That this is 48. Clear? Now we will apply region x is greater than 12 and less than 18. So put x is equal to 18 in equation number 4. This is the equation number 4. So 18 minus 18 will be equal to 0. So moment is equal to 0. So it means that x is equal to 18 inch. You will have moment 0. Okay. Now you can see shear force is a second degree curve. So bending moment will be also a third degree because there is a cube and this slope is decreasing. Clear? This slope is from this region till this region. The slope is decreasing, but this area is positive. So bending moment will be a third degree curve, and it will be like this. It will be somewhat like this. It will be a curve. Okay. Now again you can see this shear force is a curve of second degree. So bending moment will be like this. It will be like clockwise, in clockwise direction. Okay. And here you can see that the shear force is a horizontal line with 0 degree. So bending moment will be 1 degree higher. And since this is negative area, so slope will be decreasing. And it will be a linear line joining these 2 points, straight line. Clear? Okay. So this length is 8.94 feet. This length is 12 feet. Here this length is 18 feet and this is 0. And that is your bending moment diagram. So this was all about this problem 6-20. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.